I want you to take a second and just look around you right now.
Mm,
Like, seriously, look at the shirt you're wearing, or, the upholstery on the chair you're sitting on.
right.
Or maybe you're in your car. Look at the seats, the interior lining. Even if you're on a plane, consider the aerospace textiles lining the cabin. We rarely give a second thought to how these, flexible materials conform so perfectly to three-dimensional shapes.
Oh, absolutely. We are just surrounded by these highly engineered fabric-based products at almost every moment of the day.
Yeah.
You've got marine textiles, industrial composites, automotive interiors, and, well, consumers obviously focus on the aesthetics or the brand name, but the reality of producing those items at scale is just a masterclass in industrial engineering.
Totally.
Because a brilliant design is really only a fraction of the battle. The vast majority of the work is, it's the process itself.
And today's deep dive is a mission to unpack that exact process.
Okay, let's unpack this because we are going to fully deconstruct the highly technical, step-by-step journey of sewn product manufacturing.
Mm-hmm.
We're tracking the workflow from just a conceptual sketch all the way to the finished product you use every day.
Right.
We are working off this massive, really extensive stack of source material, detailing the technology and specifically the solutions offered by velocity plotters and cutters.
Yeah, it's fascinating stuff.
The goal here is to figure out exactly what is happening on the factory floor, the mechanics of, why these specific machines are deployed, and the enormous economic benefits of optimizing this entire workflow.
And setting the stage here, understanding this progression is crucial. Because in this industry, the workflow is strictly sequential.
Meaning step A has to be perfect before step B?
Exactly. If your data is corrupted or, say, poorly translated at the design phase, that error compounds exponentially by the time the fabric is actually being cut. You just cannot brute force a bad process into a profitable product. Right, so every product begins long before a cutting blade even touches the raw material.
Yeah.
A designer develops an idea, they evaluate prototypes, and eventually that 3D concept, whether it's, a tailored jacket or a bucket seat for a sports car, it has to be translated into two-dimensional flat geometry.
Which is incredibly complex on its own.
Right. The product gets broken down into individual pattern pieces inside a CAD system, a computer-aided design system, and these flat digital pieces, they become the absolute foundation of the entire manufacturing run.
Right. And that digital translation is pretty standard for new companies today, but we have to consider the reality for legacy manufacturers.
Oh, right. The older guys.
Exactly. Many automotive upholstery shops or heritage apparel brands, marine canvas suppliers, they've been in business for decades. They built their entire companies before CAD was ubiquitous.
Wow. Yeah. So they don't have digital files.
Exactly. Their intellectual property isn't sitting on a cloud server somewhere. It's sitting in a dusty warehouse in the form of physical paper or cardboard patterns.
Just mountains of them, I'd imagine.
Massive archives.
And over time, cardboard degrades, right? Edges get soft from repeated physical tracing, paper warps with humidity. So looking at the velocity plotters and cutters documentation here, they highlight their V-Shoot digitizing camera system as the solution for this exact problem.
Right, the V-Shoot.
And it seems the major advantage isn't just taking a picture of the pattern, but completely bypassing the traditional digitizing board. Because having a technician manually trace hundreds of complex curves with, like, a magnetic stylus on a board.
Oh, it would take months of manual labor.
Right.
Months. And it introduces human error every single time someone's hand slips. So the V-Shoot system shifts all that workload to a specialized overhead camera setup.
Good.
It captures those physical paper patterns visually and just instantly converts those shapes directly into manufacturing-grade digital vector files that are completely ready for the CAD system.
But wait, overhead cameras inherently suffer from lens distortion though, right? Like a straight line on the edge of the optical field usually bows outward, like a fisheye effect.
Yeah, optical aberration.
So the V-Shoot software must be heavily calibrated to flatten that out. Otherwise, a perfectly straight seam on the original cardboard wouldn't translate to a mathematically straight vector line in the software.
You hit the nail on the head. The calibration is incredibly strict for that exact reason. We are talking about millimeter-accurate vector extraction here.
Wow.
The camera system basically identifies the perimeter of the pattern. It completely ignores the background table and maps the exact geometry into the digital space, correcting for any of that lens distortion.
It makes me think of, like an archivist preserving historical media.
Okay, how so?
Like if you have a massive, priceless collection of master-cut vinyl records, you wouldn't hire musicians to come in and re-record all those songs from scratch just to get them on your phone, right?
Right, that would be insane.
You use a high-end turntable to digitize the analog source directly into a high-res, lossless audio file.
That's a great analogy.
And the V-Shoot essentially does that for physical manufacturing. You preserve the really subtle analog adjustments that some master pattern maker made to a collar, 20 years ago.
Yeah.
But now it's in a format you can instantly manipulate, grade into different sizes, and literally email across global supply chains.
Exactly. You secure the legacy IP without paralyzing your current business operations. So once that digital library is established and pristine, the workflow shifts from preservation to material preparation.
Okay, moving down the line.
Right. We move into the phase the industry calls marker making or nesting.
Nesting. Right, so now that we have accurate digital vector files, we have to figure out how to actually place them on the raw material to maximize yield.
It is the exact science of efficiency.
And looking at this, nesting algorithms are essentially solving a massive computational geometry problem. You are evaluating literally thousands of permutations to arrange these weird, complex, curved shapes across the specific width of a fabric roll.
And the computing power required for modern nesting is just substantial because the algorithms aren't just looking at negative space like a game of Tetris.
Right.
They have to respect physical structural rules. Fabric is not a uniform isotropic material like, say, sheet metal.
Meaning it behaves differently depending on how you cut it.
Right, it has a weave
Hmm.
or a grain.
Which introduces some pretty strict orientation constraints. Like, you can't just rotate a jacket sleeve piece 90 degrees to make it fit into a blank space on the marker.
It's absolutely not.
Because if you do, the warp and weft of the fabric will be completely misaligned on the final garment.
Yes.
And that sleeve will literally twist around the wearer's arm after the very first wash.
Exactly. Or consider one-way fabrics, things like velvet, corduroy, or fabrics with directional prints.
Oh, like a floral pattern that has to face up.
Right. The nesting software has to lock the rotation of every single piece so they all face the exact same direction on the roll. That restricts the algorithm heavily, making it exponentially harder to find a layout that minimizes waste.
So why do companies spend so much time and money on this step? The economic scale here is what justifies this level of computational scrutiny, right?
Absolutely. Because the fabric itself is almost always the single largest production expense for a manufacturer,
More than machines?
often far outweighing labor or machine depreciation. You're buying raw material by the yard on these massive expensive rolls. So anything that ends up as negative space in that marker, the gaps between the pattern pieces, that's just going straight to a landfill.
Wow, literally throwing money in the trash.
Exactly. When you are running 10,000 yards of, say, specialized aerospace composite or really high-end marine canvas, a material yield improvement of just 1 or 2% is massive.
Really, just 1%.
Oh, yeah. The algorithms in the CAD systems squeeze the pieces fractions of an inch closer together. Over an annual production cycle, recovering that 1 or 2% translates directly to the bottom line, often saving hundreds of thousands of dollars.
That is wild.
The nesting phase basically dictates the profitability of the entire production run.
Okay, so the software has generated this highly optimized digital marker. We have our 2% yield improvement securely locked in on the computer screen.
Yep.
But this creates a physical bottleneck. How do we extract those exact shapes from the physical roll on the floor without losing that 2% margin to human error during the cutting phase? Like, we have to bridge the digital and physical worlds here.
And this brings us to plotting.
Plotting, okay.
The digital marker has to be translated into a physical blueprint that the actual operators can use on the factory floor. And Velocity Plotters provides the Velocity Pattern Plotter for this exact transition.
Right, the pattern plot.
It's basically a wide-format industrial printer designed to output full-size paper markers, literally laying out every single piece exactly as the nesting algorithm arranged them on the computer.
And the physical scale of these plotters is serious. I mean, based on the specs, they're printing across the full width of the fabric, which could be 72 inches wide or even more.
Oh, yeah.
And the markers themselves can be 10 or 20 yards long. The paper feed mechanisms on these machines have to be flawless so the vector lines don't skew over that massive distance.
The hardware definitely must maintain structural integrity, yes. But equally critical is the data, the metadata that the plotter prints inside those vector outlines.
It's not just printing blank shapes.
Not at all. The plotter prints the part names, the style numbers, and the size information directly onto the paper blueprint.
And crucial technical indicators for the assembly operators down the line, right? Things like drill holes for pocket placements and notches.
The notches are absolutely vital.
Yeah, because if a sewing operator is attaching, say, a curved sleeve head into an armhole, those two curves have totally different mathematical lengths.
Right.
The operator basically has to ease the fabric together as they sew. And without perfectly plotted notch marks telling them exactly where to align the two pieces at specific intervals, the fabric will pucker. It'll look terrible.
Exactly. The plotter takes all that critical intelligence from the CAD file and stamps it right onto the physical paper.
And Velocity Plotters also offers kind of a hybrid solution for environments that demand really rapid development, right? The Velocity Pattern Plotter Cutter.
Yes, the plotter cutter.
It prints the full array of metadata, but it also features this specialized blade mechanism that actually perforates the outline of every pattern piece on the paper as it prints.
It's brilliant for specific use cases.
You essentially create a massive, customized tearaway sheet. So instead of an operator standing at a table with a pair of shears, manually cutting out paper templates from the plotted roll, the perforated pieces just pop right out.
Exactly. And they can be immediately laid onto, say, a specialized hide of leather or a really small run of custom fabric for hand tracing.
It accelerates the transition from the plotting phase right to the cutting table, which makes sense. That's highly advantageous for sample rooms and bespoke manufacturing where the speed of iteration is prioritized over everything.
Right.
But, let me challenge the premise of this workflow for just a second here.
Go for it.
We have highly sophisticated CAD software running complex geometry, and we are outputting perfectly optimized digital data.
Yes.
Why are we introducing a manual cutting phase at all? Like taking a handheld electric rotary cutter or a straight knife to manually follow printed lines on a piece of paper? It feels archaic in a world of robotics. Why isn't every modern factory entirely automated by now?
That is a great question, and it's an assumption a lot of people make. But the idea that automation is universally superior kind of ignores the economic reality of capital expenditure and production volumes.
Okay, unpack that.
Manual cutting actually remains a highly proven, very cost-effective process for specific business models. If you are a startup, or let's say you run a custom automotive upholstery shop that processes just one unique leather hide at a time,
Right.
dropping a massive capital investment on an automated cutting machine completely degrades your return on investment.
So the volume simply doesn't justify the depreciation of that expensive equipment.
Correct. By utilizing a printed marker from a velocity plotter, a skilled human operator using a straight knife or rotary tool can still execute the exact mathematical perfection of the CAD nesting.
Because they're just following the printed line.
Exactly. The printed lines dictate the efficiency. So
Yep.
flexibility and low overhead often far outweigh raw cutting speed in those bespoke or short-run environments.
But that dynamic completely flips when a manufacturer needs to scale up, right? When you move from bespoke, one-off orders to mass production.
Oh, absolutely.
Say you're fulfilling a contract for 50,000 identical car seats. Relying on human hands to trace printed lines obviously becomes the major bottleneck there. You demand speed, absolute consistency, and efficiency.
And this is the threshold where manufacturers migrate to automated cutting systems. The workflow paradigm completely shifts here because the automatic cutter bypasses the visual interpretation entirely.
It does look at the paper.
The machine does not look at printed lines at all. It communicates directly with the CAD system, ingesting the digital vector coordinates to drive a high-speed, computer-controlled cutting head.
Right, and Velocity Plotters and Cutters segments their automated solutions into two distinct categories based on that production volume. First, you have their single-ply automatic cutters.
Yes.
These are engineered for rapid prototyping, made-to-measure garments, or environments where you basically only need to cut one single layer of raw material at a time, but with exceptional speed and zero manual labor.
They are highly agile machines, perfect for those scenarios. But the true heavy lifting of the industry occurs with high-ply automatic cutting systems.
High-ply, meaning many layers.
Exactly. High-ply indicates the capability to cut through multiple layers of material simultaneously. We're talking about stacking dozens, sometimes over 100 layers of fabric into a massive block on the table and processing them all at once.
Which introduces a massive physical challenge, honestly. Just think about the physics of cutting for a second.
Right.
If you take a sharp kitchen knife and press it down into a loose stack of paper or like a deck of cards, the layers don't just sit still.
No, they splay out.
Right, they slide away from the lateral pressure of the blade. So if a high-ply machine just dragged a reciprocating blade through 100 layers of loose denim, the bottom layers would completely shift.
It would be a
It
disaster.
would ruin the dimensional tolerance and completely destroy that 2% yield optimization we fought so hard for in the CAD software earlier.
Exactly. So to counteract that lateral shift, high-ply cutters utilize immense vacuum compression systems.
Oh, like a giant vacuum sealer.
Pretty much. The cutting bed itself is porous. It's typically made of these dense bristle blocks.
Okay.
So operators lay down the fabric glides, they cover the entire massive stack with a non-permeable plastic film, and then they engage a huge vacuum underneath the bed.
So the vacuum literally pulls the air out of the porous fabric stack, atmospheric pressure pushes down on that plastic film from above, and suddenly a soft stack of fabric is compressed into a rigid, solid block.
Yes. It essentially turns the soft textile into a rigid sheet of wood.
That's incredible.
And then the reciprocating blade can plunge right through the compressed block, actually penetrating into the bristle blocks below the bottom layer to ensure a totally clean cut.
Without hitting metal.
Right. The bristle blocks support the fabric while allowing the blade to pass through without dulling or snapping against a hard metal table.
The blade mechanics themselves must be fascinating too, especially when dealing with friction. Because if a reciprocating blade is oscillating, thousands of times a minute, through 50 layers of synthetic material like nylon or polyester,
It generates heat.
immense friction heat, yeah. Without some kind of thermal management, the blade would literally melt the nylon and you just fuse all 50 layers together into a solid brick of ruined plastic.
Which happens if you aren't careful. That's why manufacturers of these high-ply systems engineer really advanced thermal mitigation.
How does that work?
The machines actively modulate the oscillation frequency of the blade based on the density and the melting point of the specific material being cut.
Oh, sorry.
They also utilize specialized blade geometry to reduce the surface area friction, and they often incorporate automated lubrication systems or even active cooling jets directly targeting the cutting head.
So the engineering ensures that the first piece cut from the top layer is geometrically identical to the piece cut from the 50th layer down on the bottom. In mass manufacturing, that repeatability is the ultimate metric of success. An automated cutter just completely removes human fatigue from the equation, it ensures incredibly tight tolerances, and it maximizes the material yield.
It does. But this advanced digital automation introduces a really interesting operational paradox on the factory floor, which Velocity's workflow specifically addresses.
Yeah, this is the part that seems totally contradictory to me. We just established that the high-ply cutter is driven purely by digital vector coordinates, right?
Right.
It has no optical sensors looking for drawing lines. It only follows the math from the server.
Yes.
So the big question is, why do manufacturers still use a plotter to print a full-length, massive paper marker, only to lay that printed paper on top of the fabric stack before the automated machine cuts it?
That seems crazy, right?
The machine completely ignores the paper.
Yeah.
It feels incredibly redundant to plot a physical blueprint when the cutting head already has the digital file.
What's fascinating here is that it absolutely seems like a redundancy if you only look at the cutting process in isolation.
Right.
But manufacturing is a continuous chain. The paper marker has literally zero functional utility for the automated cutting machine itself. The machine ignores it, cuts right through it.
Then what is it for?
The paper is exclusively for the humans managing the downstream logistics.
Because once the cutting head finishes its path, the reality of the factory floor sets in.
Exactly. Imagine the immediate aftermath of a high-ply cutting cycle for, say, an automotive interior.
Okay.
The machine has just sliced through 50 layers of dark gray synthetic suede. The vacuum turns off, the plastic film is removed, and you are left with hundreds of nearly identical, subtly curved dark gray shapes sitting in massive stacks on the cutting bed.
Oh, wow. It would just be an unrecognizable sea of fabric. Like a left side bolster piece probably looks almost identical to a right side bolster piece to the naked eye. It's just mirrored.
Without identification, the production line collapses into chaos.
I can see that.
The operators responsible for bundling these cut parts and moving them to the sewing stations, they would have to manually measure and compare every single stack against a master reference just to figure out what they're holding.
Which takes forever.
And if a bundle of size medium panels accidentally gets mixed with size large panels, the final assembly is ruined, and that error might not even be caught until the final product fails quality control.
So the printed paper solves the logistics problem.
Mhm.
By laying the printed paper marker on top of the fabric stack before the cut, the automated blade slices through the fabric and the paper simultaneously.
Exactly. So when the cut is finished, resting perfectly on top of every single stack of dark gray suede is a custom cut piece of paper that explicitly identifies it. It serves as a physical traveler ticket.
Ah, it has the pattern name, the orientation, the style number, maybe a barcode for the inventory system, and all the assembly notes right there on top.
Right.
So as those cut parts are loaded into bins and routed across a massive facility to the upholstery or assembly departments, the operators have immediate visual confirmation of what every single component is. They don't have to guess. They don't have to pull out a tablet and scan something to verify the geometry.
The paper marker acts as the sole source of truth as the product moves through the physical space of the factory. It keeps the entire back half of the production process organized, heavily reducing assembly errors and preventing the facility from just grinding to a halt. The paper survived the digital revolution because human supply chain logistics still require physical touch points.
Man, this entire progression really highlights how interlocked every single phase of production is. Looking at the velocity plotters and cutters data, it illustrates a strict, really unforgiving causality.
It really does.
You start with the design. You secure your legacy IP by digitizing with tools like the V-Shoot camera, managing that optical distortion to get perfect vectors.
Right.
Then you push those vectors into CAD to create patterns. You run intense computational algorithms to optimize your markers, hunting for that tiny fractional percentage of material yield. You print the blueprints to ensure the metadata survives. You cut, managing friction and vacuum pressure on a high-ply automated system. You assemble, using that segmented paper marker to guide the bundles through the facility. And finally, you deliver.
And whether a facility is executing a really low-volume bespoke run using a pattern plotter cutter for perforated manual work, or they are a global enterprise running high-ply automated systems 24 hours a day, this underlying architecture remains exactly the same.
Yeah.
Every step is a mandatory prerequisite for the next. It is the core industrial mechanism where mathematical precision actually scales into commercial productivity.
It fundamentally changes the way you interact with the physical world, honestly. I want to leave you, our listener, with this thought. The next time you get into your car or, zip up a highly technical piece of outerwear, take a moment to closely examine the seams. Look at how seamlessly the varied materials join together, how a rigid fabric eases perfectly into a curved one. Consider how much of that precise physical fit was dictated not just by the creative vision of a designer, but by the mathematical perfection of a nesting algorithm fighting to save a fraction of an inch on a fabric roll.
It's all connected.
There is an immense amount of invisible digital data, thermodynamics, and highly coordinated machinery secretly holding the seams of your everyday world together. Thanks for joining us on this deep dive.